In this section, we're going to look at all the facets of dark frame optimization. It's actually a confusing subject, and it is one that I do not recommend that people who are just starting to calibrate their data, or maybe you're just getting into PixInsight, this is not a place to go to first. Strongly recommend don't do that because there are requisites that you need to have in place to take advantage of this process. And there's also a certain level of attentiveness, an expectation of what you're going to get back that you need to understand in order to really take advantage of this, because you can get a result back, whether you apply optimization or not. Is it the optimal result? Is it the best result? That's something that people who are new to calibrating data or new to PixInsight won't necessarily be able to distinguish easily, but I'll be able to demonstrate that here right now. So consider how this works. As a refresher, I described this earlier in the calibration section of WBPP in some detail. Just as a refresher, here's how you can take advantage of it. Let's say you have a dark frame that's much longer than your light frame data. Perhaps the dark frame is 600 seconds. The light frame is 300 seconds. And we have this dark current, of course, happening in the course of that exposure time. The dark current is a thermal activity. Electrons are elevated to the conduction band because of the jiggling of the atoms in the bulk of the material. As they are elevated, they move around, they drop back down, and we see that extra electrons, that extra voltage, as we download the images at the end of the exposure. And the amount of it depends on the exposure time. In fact, it used to be that it wasn't really optimization, it was just called scaling a dark, because the naive way of doing this is just to look at the actual exposure time in the FITS header. If you have a 300-second exposure and you have a 600-second exposure, you know that you basically need to divide this thermal frame, this dark current, by 2 or multiply by 0.5 in order to subtract the remaining part from what was in the half-long exposure that you took, the exposure that was half the duration. But because this is a thermal thing, yes, the scaling the rate at a given temperature is going to be as I just described. We would really end up with a 0.5 scaling factor, just some number here that we multiply over here. But because it's thermal, if there is any fluctuation in temperature in the course of the exposures between the time that you took your maybe 300 second and 600 second, or even in the course of the actual exposures themselves, there's nothing magical about thermoelectric coolers. And even worse, if you don't have a controlled cooled sensor, that this factor may not be exactly 0.5 in the case that I've described. It may be 0.45, it may be 0.6. Whatever that number is, you can try to discover that number not by looking at the exposure, the ratio of the exposure times, but instead by looking at the noise that remains after you subtracted this dark. So the optimization, the way it works is that PixInsight takes this dark current, some value here of this dark current, and it subtracts it, whatever the value it is, it subtracts it from your, in this case, raw light frame, and then it measures the subtracted version of it after you've subtracted whatever level of dark current. So it measures the noise in this image. And then it does it again for a different level, for a different number of this dark current. So it's varying the scaling factor, subtracts again, measures the noise. Keeps doing that iteratively until it settles on the image that has the least amount of noise for the subtracted portion of this thermal frame. That's the optimization process. So it iteratively discovers what that scaling factor should be, and then, of course, it chooses that result to do the final subtraction here to give us our best answer. So this scaling factor then is discovered iteratively, not in any way by looking at the exposure times, but instead by looking at the noise distribution, the noise characteristic of the subtracted image that you're getting from this master dark that we're going to be optimizing. So based on what I've said, I think you can appreciate that it's going to discover some scaling factor. It may discover 0.5 or something very close. In fact, when you use dark frame optimization, you really should look in the control in the console when it's in use. Look at the weighting factor. If you have a ratio of images, the 300 seconds to 600 seconds for the dark, and it doesn't equal 0.5 for the weighting for the scaling factor, it equals 1. Well, that's not right. That means it didn't work. It means there's something wrong. So you would, unless the temperature is widely varying or something, that isn't what you would expect. In fact, I'm going to now jump out of here and let's go to, let's see how, I think I do a tab. There we go. I am going to go to here. This is the web page that describes partly the calibration process, but also it includes dark frame scaling considerations. In the example that they show here is what I'm now going to talk about next, but I just want to indicate that when you apply dark frame scaling, here's disabled and here's enabled. When I click on these two versions of the image, it is really tough. Now that's the uncalibrated. So here's calibrated and here's the difference between the two. This may not even come across on the recording, so you may want to visit this page. But the difference between optimized and not optimized, if your exposures are the same, so we're not just trying to discover this gross scaling factor, but we're really trying to optimize when there's a change in temperature, and that's the example that they're showing here. You see they had an original temperature of the chip of -10, and then they had, and that might be for the dark frame, temperature -10, target light frame, yeah. So the target light frame was a little warmer. Same exposure time, but a warmer chip. So this dark frame optimization can help minimize the noise. And I get that. And that's actually pretty darn cool because this is a thermal process, and we're going to look at the noise characteristics after you've subtracted that scaled thermal frame and see what minimizes the noise. And that tells you the scaling factor that ultimately you used. So now I'm going to go back here. Let's see, we do this. And where was I? I think it's here. Right. So what I just described is where you have an equal time. Again, you can still do this by slightly varying the thermal frame, discovering what ultimate scaling factor you need to subtract off here and give you the best result that will compensate for any differences of temperature. I mean, that's pretty cool too, to be able to do that. But now let's look at some of the consequences, because there are consequences of doing what we just described. What we're describing here, you'll notice that I've only talked about the dark current, the thermal frame, but there is more to an image than just the dark current alone. And that is an important thing to consider. So now we're going to go to PixInsight, where I'd like to show you an example of some data. So let me show you the data set by opening up here, the weighted preprocessing script, because I want to show you, this is the case example where I have data and I took advantage of dark frame optimization to do the job. So I have here some bias frames. You need a bias to do this, obviously. I have dark frames. The dark frame is 1800 seconds, but the light frames are 1200 seconds. I have to optimize. And I also have, of course, some flats. So let's look at the control panel here. And what you'll get is the result that we expect, right? We're going to get this little warning over here for our light frames that says, hey, the light frame's exposure differs from the master darks by a considerable amount. What are you going to do? Well, what we're going to do is we're going to optimize the dark. So we click this, and we can do that because we have a bias. And that's what's happening in that diagram that I showed you. I'm going to talk about the flats in just a moment. We can do the same thing, but you really got to be careful, which is the next subject I'll talk about. But here, now I'm doing this optimization. And then I, of course, have WBPP spits out those files. So it's going to calibrate those files with dark frame optimization, meaning that I'm going to be using an 1800 second dark frame and subtracting the scaled version of that, optimized version of that, from this 1200 second light frame. So now I'll exit here, and I just want to show you, well, what does one of those things look like? I need to navigate to here. Let's see, I need to go here, 2017, and then here. So I have calibrated data, light frame, registered. Any one of these files should be fine. Except for that one. Jeez. Let's be sure that... There. Okay. So if we just look around this frame, I mean, it looks pretty good. Yeah, I wouldn't be able to tell by looking at a single frame necessarily would I be able to tell when things are working correctly that everything is just perfect. And in some sense here, everything is perfect. This looks like a perfectly calibrated frame. I see no problems at all. Though the only way to compare, just like they showed on that web page, is you need to look at, you know, an example that has the optimization and the example that doesn't. But I can't do that because these exposures aren't the same time. I have a 1200 second exposure, 1800 second exposure. So what I can show you, though, is one of the effects of dark frame optimization, which is that the dark frame and your light frame are different. Not only are they different in time, but they're often different for other reasons. For example, the very nature of the fact that I'm doing this, taking advantage of this, is because I could hold on to that longer dark frame and calibrate any shorter dark frame that I want, or any shorter light frame that I want. That means I generally hold on to that dark frame for a longer period of time. That's a consequence. There was a reason I was doing that because of the programs that I was leading. I couldn't take dark frames for every exposure time that the imaging sessions were using. So having a master long dark to calibrate all other light frames was wonderful, but it came with a consequence. The consequence is that through time, hot pixels change. The dark frame and the data frame will change in their hot pixel populations. This means that the pixels that might exist in my dark frame will change through time compared to my light frame. They won't always match. Even more interesting than that is that when you do the scaling, it takes into account the scaling of the bulk of this thermal activity, but that has nothing to do whatsoever with the response of hot pixels. They have their own response to taking longer exposures. That doesn't deal with dark current. And that means that I have an expectation I am going to see more hot pixels. And let me stress this. I'm going to see more hot pixels than I would otherwise do if I had a match dark when I do dark frame optimization, because they don't match in their characteristics. And that requires another level of sophistication. So let me show you what I'm talking about. I have here all of those images ready to be integrated. So they're aligned. These images have been dark subtracted through optimization. And I am not going to I'm not going to do any pixel rejection here. See how it says no rejection? Because now I want to show you what's there to be rejected by not actually rejecting anything. Then you can see where some of these problems are. One of the funny things that happens, and this happened to me in the course of using this method of calibrating data with longer darks and dark frame optimization, is many people, users of the telescope, would see hot pixels and their minds would be blown. They would say, Adam, this data is terrible. Look at all the noise. And the most important statement that I would say now, and I think you can appreciate it, is the hot pixel population does not characterize the noise of the image. That's a separate item in and of itself. Hot pixels you expect to see when you use dark frame optimization. So let me show them to you now. Let's zoom in here and look around the image. I'm just going to scroll around and look at those things. Every place where there was a hot pixel, and you've got to think about where this hot pixel comes from. This hot pixel is in the data. It is not in the dark, right? If it's light here, it has to be in the data. That means it wasn't subtracted, which means that this hot pixel doesn't exist in the dark at all, because if it did, you would expect to see an over subtraction here, since that dark frame is longer than our data frame is. So this is just not characterized by the dark. We expect that. That's going to happen very frequently and very often. And so one of the requisites of using dark frame optimization, because you know you're going to get potentially more hot pixels, is you have to dither the frames. Now, when people are starting off in data acquisition with their telescope, especially new imagers, they typically are not dithering their images at all. And dithering, especially when you have hot pixels, requires not only that you shift it around, but you also need to have many exposures. And that's, again, not something that often people who are just getting into imagery are doing. So I hope you can appreciate now that even when it works out perfectly, even when you use dark frame optimization absolutely perfectly, you get more hot pixels, and that in and of itself is a hurdle or a challenge for people who are just starting. So I recommend match exposures first. Then you'll become more attentive and more aware of what's required and what to expect when using dark frame optimization. So now I will actually turn on the rejection method, and we will see that things do get rejected. Let's see, I don't know what the settings are. They're probably fine. Yep. Are those the default? Those are the default. Here, I'll even do a slightly more appropriate. All right, let's zoom in. This is the rejected pixels. You can see those clusters here being rejected as we expect. Now, are they completely rejected? Well, that's another question. Let's do a quick comparison here. The easy way to do that is just to take these settings here, put them here, and then we can compare the two images. So in the comparison, indeed, even at some low level here, they do get subtracted, or not subtracted, rejected. And that is exactly what we want. But that is a prerequisite that you have to have in place. Very good dithering with enough frames, a lot of frames. Here, how many do I have? I mean, I probably have 30 or more, 40. Probably 20 to 30 is a good number of frames to have so that you have a good pattern and they're all scattered around and it works. Let me show you something else, though. This particular example didn't have a very good one, but it does exist. Remember how I said a moment ago that you can have hot pixels that are not characterized in your data by the dark because there might be a difference in time between the two, which often happens because you hang on to a dark library. But you can also have the other thing where there still might be hot pixels that are in both the light frame and the dark frame, but in the dark frame, in that same position, that hot pixel is going to be a little bit brighter. And so when you subtract it, it not only subtracts out in the light frame, but it goes too far. And then you get dark things. And again, through the process of rejection, that also gets rejected. These are statistically outliers, which works out just fine. But if you didn't do that properly, or you have other problems, because this is very sensitive to getting that scaling factor right, to getting the illumination right. All kinds of things need to be right in order for this stuff to drop out. If it's not done well, you'll find that all of these problems remain, and then it looks like, there's this big problem with images. And this is what I saw both on the forums and in my experience with people who are perhaps getting into imaging and or starting this. They may have been doing it for a while, but they always seem to have this problem with the data, with this kind of stuff. This is where it comes from. It's a part and parcel to using dark frame optimization. Just before I leave this image here, I again just want to state that this stuff is not noise, not in the normal sense of what we're talking about, a random kind of noise, literally, that is affecting our image, but instead it does deal with this population of pixels that are acting differently. Certainly, if we didn't take care of it properly, it would impact the image and make it, not usable. But it isn't noise. So again, I just want to stress that. And there are ways, of course, of avoiding this. But it is something that you certainly need to deal with. Consider also that, just something that would compound the problem is when you use cosmetic correction. Cosmetic correction you're going to use on your light frames, right? But that wouldn't be in place on the dark frame that you're subtracting from the light frame that has, cosmetic correction or not. So there are a number of complications that go into this, and it just needs to be understood that this all comes with the use of dark frame optimization. Now, I'm going to show another element of dark frame optimization here, which is that when you consider, let's see, where am I here? Yeah. When you consider what's going on here, oh, that's not the presentation. There's a presentation. When you consider what's going on here, I think that you can appreciate there is something that is mathematically true, which is that it is easier to determine this scaling factor the more stuff you have to work with. So the more of this dark current you have to measure, the easier it is to subtract it and then measure the noise, which will also be noisier just by virtue of the fact that you have more, potentially more stuff there to work with, more signal, more whatever. And that leads to the next subject, which is, I've just been talking about light frames here, but consider if you're not talking about light frames. Remember, we also have another kind of light frame, but they are flat field images. These are light frames that are very short in their exposure time, which means that their dark current is also very low if it exists at all. And that leads to another issue. So I'm going to do this and then go to, let's see, here. And then let's look again at WBPP. So here's the control panel. You know that we have properly calibrated, and you saw me do it there, the light frames. But what about the flats? Now the flats are 3-second exposures. The dark frames are 1800 second exposures. Can I use that dark frame through the process of optimization to subtract the appropriate amount from a 3-second exposure? Yes, kind of. You can, but I don't think it's a best practice. I would argue that when you have frames that have significant amounts of dark current, it makes a lot more sense. So everything I think I've said up until this moment right now, I think is pretty solid. What I just said, maybe there's some expert out there that can argue the point. That what I'm arguing here is that I don't think it's as good an idea to calibrate very short exposures with very long dark frames, because what will happen is you have such a small number here in terms of a dark current. Any error that you might have in the process of this dark frame optimization, you can over or under subtract whatever that thermal frame is. And it's especially sensitive to flats, because once you've made that first error, that error gets multiplied by the flat when you try to apply it to calibrate your data. So my recommendation is to not do the following. Don't optimize for flats. Either, my recommendation is if you have the right kind of frame, you would use the bias itself. You just subtract off the bias. Or if you think there is any dark current in there, you make a matching dark frame, otherwise known as a flat dark. So matching or bias for flats for well-behaved cameras, I have seen so many people have so many problems where they try to do optimization. It used to be that the script would say something like there's no correlation between the flat field image and the dark frame. What it was saying is that it can't calculate a number that really optimizes that because there's no dark current, there's nothing in that flat field image of consequence. It isn't significant, the amount of change that there is. So what do? What scaling gives up? It says there's nothing to subtract there from your flat. Maybe that's true and maybe that's not, and that's what causes the problem. So when that problem exists, anytime you introduce a slight offset, you either over subtract or under subtract some amount from your light frame data, and this could be through bias subtraction or dark subtraction, or thermal frame, whatever, then that pedestal gets multiplied and affects the flat fielding so that you end up with these kinds of problems. This thing on the left can be an issue if it doesn't get that scaling factor right. That's what you need to look out for. And so the number one thing when people would ask, oh, my frames look like this, and the first thing you say, are you optimizing? And they say, well, yes, I am. And I say, stop doing that. And then they go, oh, and then it works out okay. So that scaling factor, very, very sensitive when it comes to flats and getting the flats to work correctly, because it needs to really be a precise answer. So, but as I say, I'm going to put a big asterisk across everything I just said. Maybe I'm wrong about this, but this has been my experience, is that there are cases where it does not come up with exactly the right answer, and you end up with this, you turn off optimization, and you match, of course you have no problem. So looking back at our PowerPoint, here's basically what I'm trying to describe for flats. So now we're not talking about a light frame. This is you can see I've written the word flat here. So we have a whole bunch of flats. We do this dark frame optimization, but the problem is, do you see how small that little dark current is? And I've only put it there just to maybe hint that it might be there. But of course, if you remember early on in my demonstrations, I was saying that a flat basically might have 0 dark current. If it's short enough for many of these well-behaved sensors for some short period of time, maybe less than 30 seconds, there might be nothing there at all. So what are you going to do? What's the point of this activity here? Well, I don't know. And so that's where a problem might happen, is that, this thing basically it needs to calculate a K which equals something like 0, so it doesn't subtract off anything. And if it doesn't calculate 0 or something very, very small, then it can leave something to be subtracted, and that causes a problem, which means your master flat is affected. And then, of course, when you use the master flat to get a calibrated light frame later, this is now this master flat that was created through this process. This master flat then, won't calibrate your data perfectly, and that's how you end up with the problem that I displayed a moment ago. So, continuing with this idea of the optimization of flats and how I don't think it's a good idea in general, because I have seen, again from experience, time and time again, that people have this problem with the flats not doing their job, either because you get a result that looks like this, or maybe they just don't remove enough of the problems in the image, like the dust donuts and things like that. So I went through this experiment. I just showed you the data. And all I did is I changed the fact that instead of subtracting the bias straight up, I chose dark frame optimization. I optimized the dark frame to subtract from those 3-second flats. And then what do? What's the result when you integrate all of those frames together? See, in any single frame, you wouldn't notice there was a problem. It's only when you combine them all together that suddenly you see, oh, there's a difference. And so let me show you what the difference is. So this is the integrated result. Here's the integrated result we know from using the bias subtracted flats. And here's the integrated result that you get when you have the optimized dark subtracted flats. And if I zoom out, you'll notice that there's a difference. So let me match these two like this and blink them like this. Do you see how many of the features of not only the frame, globally, illumination, but some of those dust donuts and things, they're not calibrated nearly as well. Now, I'm going to argue that this thing at the top is terrible. Even in the bias subtraction, it's not perfectly calibrated. but it is. I mean, it is. This dust donut here goes away, and lots of other dust donuts, if you zoom in, there's one that's right here. They are properly calibrated in a bias subtracted flat, whereas they are not with the optimized version, optimized subtracted flat version. I don't know what more I can do to prove it. I mean, again, there might be an expert that comes on and tells me, Adam, you are just wrong. I welcome it. Come on, let's see. I don't know what it is I can do other than demonstrate by the data that this is a potential issue, especially for people who are not necessarily looking for these kinds of subtle variations. So, in summary, let me say what I believe to be true as good practice about dark frame optimization. So here is what I would say would be the best practices for dark frame optimization, kind of a summary of what I've been trying to convince you of. First, you'll want to check the console for the scaling factor whenever you do this thing. Actually look in the console and make sure that it makes sense, it's expected. If, for example, you're optimizing exposures that are the same exposure time, you wouldn't expect there to be a big difference, right? Unless your temperatures are really wildly different. You might expect scaling factors that are maybe a little bit less than 1, maybe a little bit greater than 1, but you wouldn't expect 0.5, for example. And then the second thing is to expect consequences of hot pixels by virtue of the fact you're using dark frame optimization. It means that hot pixels won't be subtracted in the exact way that you might expect. And I just want to stress this idea that hot pixel populations are not random fluctuations. They're more like a fixed pattern noise in that sense. Based on the above, dark frame optimization then, for light frames, requires many dithered images for good rejection of those hot pixels. And then, choose to calibrate flat field data with either biases or matching darks. That's the recommendation I say. In general, don't optimize darks for the purpose of calibration of flat fields. If you do, and I just demonstrated in my own data, it doesn't work. If you do, boy, really pay attention to what you're getting. You really got to be able to identify that this is an issue. You can do exactly what I did. You can do with and without that optimization, if you, with the bias, and see which way really calibrates the data better. And then finally, check the calibration workflow diagram. I should have added the diagram there. In addition to the checked boxes in the WBPP control panel, just to be sure that, if you weren't paying attention, that you are or are not using the dark frame optimization. So going back here, I'm just going to load, because I didn't show it earlier, so I added that to my little summary. I'm going to show here that where I am employing dark frame optimization, if we go to the control panel, click on one of these things there, then show the diagram. Oh, I'm not doing it here. Let's see, am I doing it here? Dark frame optimization, yes. So I'm doing it here, which means you'll see the K shows up. If we instead do not use dark frame optimization, you wouldn't see a K. So in the case of the flat, right now I'm not using dark frame optimization here, because this is a master flat. That's why I'm not using it. Let me just load those flats again, because well, here they are. Let's just remove this guy. And then we should have a group of flat. Yeah, so here's the flats, right? And if we do not optimize here, we're going to say it differs. But then if we don't, well, so let me show you the full set of examples. Here's the case where we're not optimizing, we're not using a dark, this is using the bias. So if we show the calibration diagram, we can see it's using the bias. So what happens if we do a dark frame, but we don't optimize? What does that look like? Well, that looks like this. And this is not what we want, okay? What this means is it is going to literally be subtracting from our flats a dark frame that is 800 seconds long in exposure. It is not scaling at all. There is no scaling happening. How do you know? Because there's no K here. What this is doing, I know there's a bias here, but sure, subtracting the bias, which means we subtract off the bias and the current. Well, that is the dark current, the thermal frame. That's the whole master dark. These two things, the green and this gray is this whole thing right here. So I will be subtracting this from this, and that doesn't make sense. Instead, what you could do is this, but I just demonstrated, not a great idea, not for flats, but this is the correct way in terms of optimization, because now you can see the K. So maybe you think, oh, Adam, come on, what does this matter? Does this really matter? Do people really do this? One moment. I extracted this image from the forum because someone had a question and they created a screenshot. I apologize, it is a low resolution image. But their question was, why were their flats not working? And you can see exactly what's going on here right now. You can see that the flat here, which is 20 frames or whatever, when it creates that master flat, it will be doing so by something that's even worse than what I've demonstrated, which is that optimization requires a bias. Without a bias, I'm not even sure exactly what to say about this. This is going to try to subtract the whole dark from this thing and optimize the result to give you the lowest amount of noise. Of course, that doesn't make sense at all because the entire dark frame itself, a 600-second dark, contains both the bias and that dark current. So that isn't really scalable in and of itself because the bias is some pedestal value. So the error that you get over, not error, but the warning that you get over on the right is saying that this configuration should be avoided. I mean, now there's a judgment because you really should have a bias frame. This stuff matters. The idea of using bias frames to optimize darks, it matters. Because this happens often with people who are just getting into imagery. And so I hope I've persuaded you that the use of the optimization of darks, it's a cool thing to do. And I used it for years in the course of the remote observing astrophotography that I was involved in. But I did so with this extra attentiveness to what was going on. So I would just recommend now going forward, hopefully, by looking at this section, you can see some of the things to look out for. You can see when you've properly configured it, and you can see when maybe others post something like this that you can see directly in their control panel whether it's going to work or not. So I recommend only doing dark frame optimization for light frames that are significantly long. And of course, being configured properly, you have to have that. You have to have the bias in order to be able to do it. So I hope you enjoyed this kind of deep dive into optimization. I don't know an easier way to explain all of these effects without showing you some of the examples that I did. But I hope it's beneficial, and I hope it will avoid some heartache that people often have when trying to take advantage of this operation.